Hello everyone, welcome to week 5 of this course. So in the last week we discussed about recurrent architectures, and this week we will discuss about transformers, and that has been the main architectures for NLP since its inception in 2017. So in this lecture I will introduce the transformer architectures, and we will just start. It will take few more lectures to complete this discussion. So we will start with attention as a more general framework. We will talk about transformer as an encoder-decoder framework directly, and we will focus on one particular part, that is self-attention inside transformers. So this was a 2017 paper from Google Brain at that time and Google Research and University of Toronto that introduced this paper, Attention is All You Need. That's where the transformer architecture was brought to the field. And since that time, it has shown results in not only NLP, like this was just the paper, 2017 paper, that showed that compared to all other different architectures, which include RNN, convolution and different methods, transformer was able to perform better. This was just the first paper. Okay, it was able to perform better than all other architectures. And even if you see the compute, the training cost, it was smaller than all the competing models. So this was a huge boost, that you can train this much more efficiently and you can actually achieve a better performance. And now coming to 2024, you would see that most of the models that are performing well on the benchmarks like chatbot arena are based on transformer architecture. So you will see all the GPT-4 models and others that are based on transformer architecture. Okay, and include from various different companies. And it's not that transformer is only applicable to NLP domain. It has been applied to various different domains. For example, the work you would have heard about protein folding, that has transformer as its one of the basic components. Image classification, so transformers were applied as vision transformer. There are transformers applied to audio, like audio transformer, and they have been applied for various different things like ML for systems. So you see transformer model typically performs better. So they have shown promise outside NLP, and that is why they have become hugely popular. So a quick recap on the attention architecture, attention method that we discussed in the context of recurrent neural networks. So we talked about attention in very, very specific context. That is, you have an encoder-decoder architecture, and the decoder can attend to all the encoder states, and that's how it can get a better contextual representation every time. So every time it can attend to all the encoder states and get a context, and it will be dynamic, right? Every decoder state will get a different contextual vector. Now, attention is not just limited to this. It can be applied to many, many architectures and not just sequence to sequence that we have seen. Okay. More generally, you can see attention as a way in which you are given a set of vector values. So in this case, these were the vector values, the hidden states of the encoder, and a query. Let's say this is the query, right? So you have some values and you have a query. Attention is a way in which you can compute a weighted sum of the values. So you can see what is the weight I should give to different values. Accordingly, I obtain a weighted average of the values dependent on the query. So this is what attention does in general. And we can say in general, query attends to the values, right? Now in this particular architecture, we saw that the hidden state of the decoder was the query, and it attends to all the encoder hidden states, the values. Now, it's a very general technique. So given this particular definition, I can think of this weighted sum as some sort of selective summary that I am getting for the information that I have in the values. So I am getting a selective summary from the values, and that's where the query would focus on. So I can say if I have some values V1, V2, V3, I have a query. The query can select whether I want to focus on V2 or V1 or V3 by putting some attention weight. So I can say, okay, 0.7, 0.2, 0.1. So I'm focusing more on V2 and less on V1 and V3. So if you think about it, attention is a way in which you can obtain a fixed size representation of any arbitrary set of representations. And that's what you can think in terms of transformers. You think about any arbitrary set of representations, and you can use attention to obtain a fixed size representation. And that's why, although we will start discussion about transformers in the context of language, where we are using the word representation as the input, even if you can replace it by images and any other modality, and you can get a representation as input, you can use transformers to be able to attend over that. So I will obtain a fixed size representation from an arbitrary set of representations, right? So that is what we will do. Now this is something we had already discussed, that what were the problems with the recurrent architecture. So one was that between any two distant words like the chef and watch, there is no direct connection. So the interaction between chef and watch has to go through all the steps in between. So you would compute one hidden state at a time, and only when you have computed this hidden state, then you can compute this. So there is no direct connection from chef to watch. So there is always a linear order of the words in the case of recurrent architecture. And that creates problem in that you cannot parallelize the computations. So you cannot compute all the hidden states in parallel. So you have to first compute H1, H2, H3, because there is a dependency. So H2 depends on H1 and so on. So HT cannot be computed unless you have computed HT minus 1. Right? And this dependence creates a problem in doing large scale training. You cannot parallelize these computations. So then transformers give a method by which you can solve both of these problems. That is, you can have a direct connection between any distant words, and you can do things in parallel. So you don't have to compute hidden state for each word one by one. You can do everything in parallel, right? So we will see this. Okay. So this is what is achieved through attention. So that's why the paper was attention is all you need. So you don't need this recurrent connection anymore. So what will happen, given a word as a query, attention can be used to access information from a set of values. That's a general notion. Now we were doing it from decoder to encoder previously. But what about doing it within a single sentence? So think about just the encoder, right? Can you do attention within an encoder itself? So you will have in encoder different embeddings. So can it happen that one word attends over all other words? And can it be used to compute better representations? Right. So here that's what we will see. All words can interact with each other, and because of this region, because you don't have a linear order, you can do things in parallel. Okay. And this is what we will see in detail, that all words in the case of attention mechanism, all words in one layer will tend to all words in the previous layer, and that's why there is no sequential dependency. So transformer paper introduced this as an encoder-decoder architecture. So they use it directly for machine translation and tasks like that, where you have to use some sequence to sequence framework. So we will study from that point of view it as an encoder-decoder architecture, but later we will say we can use it only as an encoder as well, also only as a decoder, and lately this has been the most prevalent form of transformers, that using transformers only as decoder models. So what transformers encoder actually do? So encoders will produce a representation of the source sentence. So suppose this is the source sentence in French. So encoder will be used to produce a robust representation for this, a very sophisticated representation. So you will have a representation for the first word, the second word, and the third word. Okay. So this is what we saw in the RNN encoder also. You have an input and you get a representation for all the words. So same thing is being done by a transformer encoder as well. So you are being able to produce representation for each word in the input by the encoder. And now these representations are now used to condition the decoder that will help in generating the output. So this will be used by the decoder to generate the output, and the generation is again in an autoregressive manner that we saw in the case of RNN. So decoder will generate one token at a time to produce the target sequence. So if I see this picture, it looks like exactly similar to RNN, right? So if you think about this as a black box, so RNN also does that. You have an input sequence and you produce a representation for that, each word in the input, and then you use that to decode into one token at a time. Right? But where is the difference? Difference is in the underlying architecture, underlying black box of encoder and decoder. So these encoders can also be thought of as a stack of encoder blocks. So in RNN also we talked about multi-layer. So here it goes as a default, like typically you would only see like a stack of encoders and a stack of decoders in the case of transformers. So in the original paper they used 6 encoder blocks and 6 decoder blocks, right, for doing this task. And each encoder is very similar, and same like RNN, the output of the first encoder will go as the input for the second encoder. Right? So this is another visualization. So what would happen? So you suppose you are passing 2 words, thinking machines. So in the first layer, the embeddings for these words would be the input. But as you go in the deeper layers, this is the encoder 2, they get outputs of the previous layers as the input. So R1 is the output of the first encoder layer. This becomes the input to the second encoder layer. Okay. And what is maintained is that each encoder block will have the same size as the original, same size input. So suppose in the original paper this was 512 dimension embedding for the word. So you would maintain this throughout. So here in the second encoder also you maintain a 512 dimension input, and this is also called as a model dimensionality. So you fix one dimensionality and you retain that throughout. So you would always have 512 dimension input and 512 dimension output from each encoder block. Okay. So this has 2 main components that we will discuss. So one is you do self attention. There is no recurrence anymore. You do self attention, and self attention will help you obtain an output per word. So X1 will give you an output G1, X2 will give you an output G2, and then you will pass it through a feed forward neural network, and this will give you the final encoder block output. Of course, there will be many more things in between. We will see that in course of time, but these are the 2 main blocks. Okay. So now what is self attention? Right? So we will see multiple intuitions around self attention, like why is that needed and what actually it does. So let's go back to our static word embeddings, word to vec. We talked about that in the 3rd week of this course. Now we learned word to vec at some static embedding. What do I mean by that? You give me any sentence, the word it will have only one representation, one embedding. So one 300 dimension or whatever dimension vector. It will not change based on the sentence, right? So embedding of a word does not reflect how its meaning can change in context. And we know the words may not have a single meaning. They may have multiple meanings depending on the context. So that means it would have a meaning that some sort of averages out across all its contexts that have been seen in the training data. So think about the sentence, the chicken didn't cross the road because it was too tired. I'll be able to make one particular representation only for it, right? Now, what is the representation of it is not very clear. So what if I could make a different representation for a word in every new context it appears in, right? So that is the appeal, that from where the contextual embedding idea came in, that can I make a contextual embedding, that is whenever a word is appearing in a new context it would have a new embedding, right? So each word would have a different vector that would express the different meaning that are depending on the surrounding words. Now how do you compute this contextual embeddings? And attention is one of the primary methods for doing that. Of course, we will see one more way of doing that in next week, but attention is what we are seeing right now, is one of the method by which you can compute the contextual embeddings. So what you will do, for example, so we talked about this sentence, but now let's take two different sentences. So what we did here, so at this point I do not know what is the context of it, but now let's say I have the sentence. The chicken didn't cross the road because it was too tired. The chicken didn't cross the road because it was too wide, right? And now consider the problem of telling what does it refer to in the two sentences. And this is called the coreference resolution problem. And you can see this is a difficult problem because in the two sentences, only one word has changed. So you replaced tired by wide. Nothing else has changed. And you have to tell what does it refer to in the two sentences. Now we can see that it was tired, so it should refer to the chicken. It was too wide, it should refer to the road, right? But can we also learn this, right? Can we say that contextually, contextual embedding of it would actually be more, will attend more to chicken in this case, and will attend to the road in this case, right? Can we have some mechanism for doing that? So the intuition for attention is that it will build up this contextual embedding from a word by selectively integrating information from the rest of the sentence, right? So it will take from the neighboring words. So think about all the words in the sentence, for example, and see based on these words, what is the representation of this one particular word. And you can do that for all words in the sentence, okay? And we will say that a word attends to some neighboring words more than others. You will put attention somewhere, right? You will focus your attention on some particular words. So this was what actually was one of the visualization in the blog that they had after transformer paper. So you have two different layers. So think about two different, think about them as two different blocks right now. So what was seen in this sentence, the chicken did cross the road because it was too tired. It was found the word it on layer k plus 1 was putting more attention on chicken, which makes sense, tired, than the road. So this was, if this was say 0.2, this may have been 0.7. So this was much more attention on the word chicken where it should have, right? So this is what we want. So you want the words to put attention on the neighboring word so that you can get a better contextual representation, okay? So now I would note the contextual representation of it will have some weights from the chicken embeddings or the chicken representation. So a simplified version of attention, you can think like that. So you given a word, you want to get a sum of prior words weighted by their similarity with the current word. So given a word, you want to say, okay, whatever words I have seen in the sentence till now, I'll take a weighted average or weighted sum of their similarity. So suppose I am at word xi, I have seen x1 to x7 token embeddings. So I'll produce an output for the word xi ai, which will be a weighted sum of x1 through x7, right? And also I can include xi. And what is the weight? What will the weight depend on? It may depend on simple thing, for example, the similarity of xi with each of these. So I can compute the score of xi and xj as just the dot product of xi xj, and I can compute attention weights by taking a softmax over this score, and then my attention output will be simply the weighted average of the individual embeddings. That is the idea, the simplified version, right? It will be slightly more involved, but this is the idea. You take all the words and try to attend over these to produce the final representation. Another intuition for self-attention. So you can also think about self-attention as some sort of fuzzy matching, right? So what do you do there? So think about you are using a hash table. So where what will happen? So you have various keys and corresponding values, right? In the hash table, you have various keys and corresponding values. Now, how do you look up for a query? So you take a query and you hash that, and you find which of these keys it will map to. So suppose you find this query maps to this key K2, and you will then retrieve the value that is put in that particular key. So you'll retrieve V2, right? Now self-attention, what we will see, each query will match. We will do a mapping or matching with all the keys, and we will find, okay, maybe it has some degree of similarity or some degree of match with each of the keys. So accordingly, I'll take a weighted average of the values. So we'll return a sum of values weighted by the query key matching. So maybe this had these 4 had the highest matches, so they will get the high weight. Other may not even feature, like, or may have a very small weight close to 0. So I'll produce a weighted average of the values. So rather than having a single value, I'm producing a weighted average of values. Okay. And another intuition. So it is based on the key, query, and value concept. So you can think about how you search on a YouTube video. I mean, this is just some approximate intuition. So what will happen? So you are giving your query some text in the search bar, right? And you want to finally obtain a video. So what will happen? You have a query, but underlying the retrieval system, say each video is stored using some key. So they are indexed using some keys. So each video has a key, and corresponding value you can think of as the video, right? So you have, and these keys can be some metadata like channel, artist, title, and so on, right? So these are the metadata. So you have key and value. So multiple videos are indexed using key and using the keys, and what you have, what is stored is the value, that is the corresponding video. So when you give your query, typically you match it with all the keys, and you find what is the key that is matching the video the most. So let's say this query, this key matches the most. You get the corresponding value back. So this is returned to you. Now you can also think of it as an approximate matching, where you match with all the keys and say, okay, K2 has a match with a degree 0.7, and K3 has a match with degree 0.2, and K1 has a match with degree 0.1. And now you say, okay, you return me a summary of the video, I mean summary of my output. So what you will do, you will create a video which takes some 70% information from V2, 20% information from V3, and 10% information from V1, and you create some sort of trailer right out of all these outputs. So this is another intuition for self-attention. Okay? Typically you will get a recommendation results of the video, but I'm just saying, suppose you want to create a summarized output from all the videos. So this is what attention will look like. Okay. Now coming back, so we have some intuitions for attention. Now how does it actually work, right, using equations? So what are we seeing? So we will start by inputting vectors like x1, x2, x3, x4, right? But we will not work with these vectors. What we will work with? We will work with query, key, and value. Right? So we will use the query. We will compare the query to various keys, and based on the match, I'll use their values to give an output. Right? So I'll have query, key, and values, and I'll get a weighted sum of the values as my output. So I'll weight the values, and that will be my output, right, for a particular query. So something like, so now if I am seeing what will it attend to in the previous layer, I should have some way of finding the query from the word it, right, and all the words, right, on which I have to attend should be denoted by keys and values. So there will be K1, V1, K2, V2, K3, V3, and so on, up to whatever word. You will have some keys and values for all the words, and this will happen for the entire sequence. Okay, and now you will use the query to attend over the keys, and based on the attention, you will take a weighted average of the values. Okay, so this is how an actual attention head looks like. Right? We call it an attention head, and we will see, right, we can also generalize it to multiple attention heads. So what we will have? So suppose you feed in the input in the first encoder layer. This is just the embeddings, xi vector. You will create query, key, and value from that. Now how would you do that? You will simply project it by using various matrices. So let's say you have 3 different matrices. They are all learnable parameters. and you will use that to project each vector into query, key and value. So I can simply multiply with key matrix and I'll get the corresponding key. I multiply this vector with value matrix, I'll get the corresponding value, and so on. So from the same vector I can obtain query, key and value, right? So I introduce some learnable parameters, like what are the best possible query, key and values that will help me achieve a particular task, right? Let the model learn that, right, from the task objective. Now, so that means I have now 3 representations of the word xi, right? Then I will compute similarity of the current element xi with some prior element xj, and actually we will see you can do it in encoder to the entire sequence, and we will use dot product between the query of xi and the key of xj. So I'll compute dot product between qi and kj, and instead of summing up xj, we will sum up the corresponding values vj. Okay. So let's look into more details by another visualization. So let's say I have this input, the beetle drove off, okay, and I get the embeddings for all the words. So this is embedding for the beetle driven off. So what will I do? So let's say I have 3 matrices, the query matrix, key matrix and value matrix. I'll use that and multiply with an embedding to get the query, key and value. So I can do that for, I have done it for the word beetle, I can also do it for the other words like the, drove and off. And this will help me in getting the query, key and value for all the words in the sequence, right? So I have q1, k1, v1, q2, k2, v2 and so on. Note that the same 3 matrices are used throughout, right? So I'll use the same 3 matrices. So I'll again use wq. I'll not have another version of this matrix. So that's how it becomes independent of the sequence length in one way, because you will apply the same matrix in all the words in the sequence and you will get the corresponding query, key and value, right? That's the first step. Next, I want to do self-attention output for the word beetle. So remember, what do? I have to get a query, and this query I'll match with all the keys in the sequence. So query is coming from the word beetle. Where the keys coming from? Keys will come from all the words in the sequence. So I have k1, its own key, k2, k3, k4. I will find similarity of this query 2 with k1, k2, k3 and k4, all the different keys. Okay. The simple dot product, right? We will see a more general formulation, but let's think about it, a simple dot product. So then I do dot products, and finally I do softmax to get attention weights. So q dot k1 up to q dot k4, and I do a softmax over that. And that's how the formulation will look like. We have done it multiple times in the course already. So you get the self-attention output lambda h. Next, what will I do? I'll take a weighted average of the values as per these weights. So I'll multiply lambda 1 with this v1, lambda 2 with this v2, lambda 3 with this v3, lambda 4 with this v4, and I'll add all of these. This will give me the self-attention output for the word beta. Okay, so I got some portion of v1, v2, v3 and v4 that are multiplication with these lambdas, the attentions over different words, right? Lambdas capture how much I am attending over different words, and I get a weighted average of the values. That is my self-attention output at this point. Now coming back to the 2 things, right, that we talked about. So we talked about 2 problems with RNNs. One is that there is no direct connection between words. But now in transformers with self-attention, this word can attend to any word in the sequence, even if it is 15 words apart, 100 words apart, right? If my memory and other things allow me, I can attend it, right? The architecture itself has no limitations. So each word can attend to any word in the sequence, right? So there is a direct connection between every 2 words in the sequence. That was not there in recurrence. So it solves that. Second thing we said, I could not compute the representation in parallel before. But now think about, there is no dependency. So while I am computing the self-attention output for the word beetle, I mean, nobody is stopping me to parallelize the things for the whole sequence. So I can in parallel compute the output for the drove and off, because there is no dependence between these operations. So I can do all of these in parallel, right? And that's what hugely boosts the training efficiency of the transformer architectures. Okay, so this was our just introduction to transformer self-attention. You can go through chapter 9 of our book to have further details, and we will discuss more from here in the next lectures of this week. Thank you.